Stonehenge, the most famous prehistoric monument in Britain, is thought to have been built over 3,000 years ago. The smaller stones, some of which weigh over 5 tons, were brought, it's believed, from the Preseli Mountains in Pembrokeshire. But how did megalithic man get them here? The most widely accepted theory was demonstrated in the 1950s, when a group of schoolboys made the task of moving huge blocks of stone look quite simple. They used logs as rollers or bearings, and the stones rolled easily over the ground. The building of Stonehenge may have been one of the first examples of the use of what today are known as rolling element bearings, and these play an important part in engineering. Rolling element bearings, as the name suggests, use a rolling action to transmit mechanical power. The load is concentrated on a small area of contact. Ball bearings make a point contact. Roller or needle bearings make a line contact. The small area of contact produces a high contact pressure, and that's why rolling element bearings are made in hard, high-strength steel with a very smooth finish. As can be seen from the shaded area on the graph, rolling element bearings tend to be used where high loads are running at fairly low speeds. This keeps wear to a minimum. But there are other examples of primitive bearings, again dating from the dawn of history. When the Egyptians began building the pyramids, they were faced with the same problems as the architects of Stonehenge: how to move massive blocks of stone as efficiently as possible. Each of these stones is as high as a man. It's thought that they devised an equally ingenious system to that used by Stonehenge man. This Egyptian mural shows a colossal statue being dragged along on a sledge. The figure at the front can be seen pouring a liquid under the runners to act as a lubricant. This idea is very similar in principle to the plain bearings in use today. Plain or journal bearings are normally used to house or support a revolving shaft. In most cases, a lubricant is essential, and this plays an important part in the operation of the bearing. We can use a model to show how the lubricant works. Normally, the shaft would rest at the bottom of the bush, but to show the way it works more easily, we've turned it upside down with the bearing weighted down onto the shaft. When the shaft rotates, it draws the oil round with it, forcing the bearing to rise, so cushioning the shaft. The pressure generated causes the oil to rise in the tubes. If we take a closer look at what happens, this time the right way up, you can see the shaft at rest in the bottom of the bearing. As soon as the shaft starts to rotate, the oil next to it is pulled along with it. However, there's no gap for the oil to go through, so a pressure wedge is formed. It's this pressure that eventually forces the shaft to rise and float on a cushion of oil. We call this hydrodynamic lubrication. We can't ignore the friction set up when two surfaces rub together, especially when a shaft is starting and stopping frequently. If a bearing is to work as efficiently as possible, you have to be very careful as to what material you use. In this standard milling cutter, you can see that the vertical force from the cutting edge is resisted by the yoke which holds the revolving shaft, or arbor. To prevent excessive friction between the arbor and the yoke, it's fitted with a well-lubricated phosphor bronze bearing. Although brass would be cheaper, there are certain problems associated with it when it's used as a bearing material. For example, if you do use brass, as the shaft stops and starts, you can see that minute quantities of the metal are transferred from the bearing to the shaft. These particles would eventually build up and cause the shaft to seize. It's the tin in the bronze that gives it the edge over brass. The tin, reacting with the oil, forms a soapy complex, and this imparts a microscopically thin extra layer of lubrication to the bearing. This hinders excessive wear. The phosphor bronze bearing used in this milling cutter is a split bearing, which not only allows the oil to circulate, but also means that any wear can be compensated for by tightening the thread. So you always have a tight fit, and excess vibration is virtually eliminated. You can hear what a badly fitted bearing sounds like. And you can see the ragged result. This is known as chatter. As well as having a low coefficient of friction, ideally a bearing should possess the best possible resistance to fatigue. Shell or thin-walled bearings are particularly well suited for the job. A strong mild steel backing is coated with a thin layer of leaded bronze or some similar material. This unites the strength of mild steel with the superior bearing properties of the coating material. These shell bearings are also quite cheap and easy to make. The mild steel backing can either be in strip form or tubular. Once the required length has been cut, the tube undergoes a number of machining operations. These prepare the inner surface and the outer rim for the coating process. Before coating, the bearing is whitewashed on the outer surface. This prevents bearing material from being deposited where it's not wanted. The coating is applied by centrifugal casting. First of all, the tube is dipped into a solder, which will help the coating to adhere more easily. Then it's clamped inside a rotating cylinder into which the molten bearing material is poured. In this case, it's a white metal made of lead, antimony, and tin. As it spins, the bearing material, assisted by the centrifugal force, coats the inside of the tube evenly and solidifies on cooling. This process can be used for a whole range of white metal or Babbitt bearing materials, materials based on tin and lead, with small additions of antimony, copper, arsenic or cadmium, as well as copper-based materials, the choice depending on the conditions under which they'll operate. Shell bearings are either used in one piece or split to make two half bearings. These would be used together in a final structure, but it might be difficult to fit a single bearing. At this stage, the bearing surface is still rough after its centrifugal casting, and it's got to be machined to the right size. This is done in several stages. First, the surface is rough machined to remove surface impurities. Then comes any additional machining. Oil grooves, for instance, which are cut into the bearing's surface. This is a job which has to be very carefully carried out, as any irregularity in the oil duct could weaken the final performance of the bearing. Last of all, a fine finish for the bearing's surface. This is done by fast machining, and the finished bearing is ready for use. Thin-wall bearings come in a range of shapes and sizes, some with a thrust face, some without. As with other hydrodynamic bearings, they tend to be used for light to medium loads at high speeds. All these soft metals have a low melting point, and if an oil failure causes a rise in temperature, the white metal melts and runs out of the bearing. Loud knocking gives ample warning of bearing failure, and the bearing can be stopped before any damage is done. An advantage of these bearings is that when operating in dusty conditions, the soft coating absorbs dirt particles, which otherwise might cause the shaft to wear excessively or seize up altogether. If you chemically treat a well-used bearing so that the ferrous debris shows up, you'll be surprised to see just how much there is. It shows up as the purple areas on this roll of paper. This kind of contamination is quite common and could have stopped an ordinary bronze bearing if allowed to build up. Babbitt metal has a number of uses and is ideal for big ends and main bearings in cars and lorry engines. Some materials other than oil have a certain amount of lubricative properties. The dry bearing properties of graphite, for example, are simply demonstrated. If you pull a heavy metal block along another metal surface, you can measure the force needed to drag it along. Now watch what happens if you add graphite powder to the flat surface. You can see that much less force is needed to pull the block along. This friction-reducing property of graphite is used to great advantage in the production of porous metal bearings. These also contain their own built-in reservoir of lubricating oil. Porous metal bearings are formed by the process known as powder metallurgy. The ingredients are stearate, copper, tin, and graphite. The copper and tin form the bronze base, while the stearate and graphite assist the lubrication. The powders are weighed to a predetermined formula and then thoroughly mixed. The powder is fed into an automatic press, which compresses it in precision dies. The particles of powder form a sort of metallic sponge. The amount of porosity depends on the pressure applied. Here it's around 185 newtons per square millimeter. At this stage, the porous compacts are quite fragile, and they have to be sintered to alloy the copper and tin. This welds the particles together, forming a porous bronze structure of the required shape. The transformation takes place in an atmosphere containing hydrogen at 800 degrees centigrade. That's well below the melting point of bronze. The result is a tough, porous structure able to withstand relatively high loads. Before sintering, the powder compact can easily be broken. After sintering, it's much tougher. After they've been sintered, the bearings are sized. This ensures that any distortion that may have been caused by the high temperature sintering can be rectified. Next, the bearings are placed in a vacuum chamber. When the vacuum is formed, all the air trapped in the porous structure of the metal is extracted. The chamber is then filled with oil, and the metal draws the oil in like a dry sponge would draw in water. The bearings, when they're removed from the chamber, will be seeped in oil. As much as 35% of their entire volume will be made up of oil. The oil content can be quite easily demonstrated. If air is blown into the bore of this bearing, the oil foams out. In practice, a small amount of oil initially escapes from the surface of the metal. The rotation of the shaft then draws more oil from the bearing. A pressure wedge is formed, which lifts the shaft. At the pressure zone, some oil is forced back into the pores of the metal and recirculated to the unloaded area. When the shaft stops rotating, most of the oil is reabsorbed from the clearance by capillary action. Obviously, the life of the lubricant itself is vital in this type of bearing, which is ideal for use at low to medium loads in the medium speed range. Use a bearing like this in a starter motor, and it should last the life of the car, without any need for additional lubrication. A nylon bearing is the best substitute when the use of oil is not permissible or possible. Most processed foods are produced using highly mechanized or automated equipment with many moving parts and revolving shafts. You wouldn't want oil getting in your ice cream or biscuits. Nylon is the ideal substitute. It's a dry bearing material which needs no lubrication, although its performance is improved even if it's only lubricated with water. Nylon and other dry bearings work efficiently under light or medium loads. They resist abrasion and chemical attack, they're non-toxic, and can be used continuously at temperatures up to 90 degrees centigrade. The smaller bearings are produced ready for use by injection molding, a quick and efficient process. For larger components, the nylon is first extruded to form large bars of the appropriate diameter. These are then machined to form the required shape of bearing. A drawback with nylon is that it readily absorbs moisture. This can be inhibited by the addition of fillers like graphite, glass fiber, and molybdenum disulfide, which, apart from turning it black, gives it increased resistance to wear and the ability to operate at higher temperatures. As with other non-metallic bearings, nylon tends to be used with a stainless steel or mild steel shaft, some of which are often chromium plated. Materials used in bearings can pop up in the strangest places. This fried egg wouldn't slide around the pan as nimbly as it does if the pan didn't have a non-stick coating. Polytetrafluoroethylene, PTFE for short, plays an important role as a dry bearing material. It's particularly useful in the building of bridges. Bridge bearings on the top or bottom of bridge supports allow for expansion and contraction, which can be up to 12 inches between the hottest and coldest day of the year. The main part of the bearing is made of a steel alloy which is carefully machined to the utmost accuracy. This concave part will house